Okay, next slide, please, Ajit. There's a couple more people just joined, so welcome. Thank you for joining. It's great to see so many people here. First of all, I'll introduce myself. So, hi, I'm Steve Lene. I'm your host. I'm an application engineering manager at SimScale, and I'm going to give you a brief introduction to SimScale before we move on to a demonstration. Ajit is going to do the presentation and the demonstration, and he's going to be the star of the show for you. Ajit's got a background of aeronautical and aerospace engineering and a master's degree in computational engineering, and he's a valuable asset to our application engineering team here at SimScale. So first of all, I'm going to give you an introduction to SimScale. We're a Munich-based company founded in 2012, and we have a global presence with millions of simulations being run worldwide. And we're funded, so we're going to be here to stay. What do we do here at SimScale? Well, we created the world's first cloud-based engineering simulation platform. On this platform, you can do fluid dynamics, solid mechanics, and thermodynamics. And the fantastic part about it being cloud-based is that everything is accessible via a web browser. We're trusted and used by thousands of organizations worldwide. On the screen here, you can see a brief list of some of the brands that trust SimScale. And how does SimScale actually help in your design process? Well, with the SimScale platform, you can accelerate your design process by doing simulation earlier in the design process. You can test performance, optimize for durability, and improve your design efficiency with our cloud-based simulation tools. How does this compare to traditional CAE tools? Well, with traditional CAE tools, you typically have high fixed costs, and there's special dedicated hardware required to run the simulations. Software is installed and it has to be maintained locally on your hardware. And also, the CAE tools are built for specialists, which means that you have to have detailed training, and you usually need a vast amount of experience to be able to get the most out of the complex software. Typically, computation time is measured in days or weeks, and it's not very easy to run parallelized simulations. That's because your hardware and your software is occupied during a simulation run. How does this compare to SimScale? Well, the benefits of SimScale are that there's no upfront investment required. There's no installation or maintenance of hardware or software. The setup is really straightforward. All you have to do is create an account, log in using a web browser, and you're set. You can seamlessly collaborate with your teams in your organization. And at SimScale, we provide world-class support. There's a support system built into the software so that you can access our experts to help you with your simulation. Typically, with our platform, computation time is measured in minutes rather than weeks. And because we're leveraging the capabilities of high-performance cluster cloud-hosted computing, you can run as many simulations in parallel as you like. Okay, that's the introduction from me, and I'll hand over now to Ajit to do the demonstration.
Thanks, Steve, for the introduction of SimScale. And this is Ajit. As Steve mentioned, I work as an application engineer here, and today we'll be looking at a thermal comfort simulation, and especially about a classroom thermal comfort that we'll take a look during this demo session. At first, let's look at our agenda. So the first session will be about introducing to the thermal comfort indices. So we have two major indices that could actually account for a thermal comfort inside a classroom. And next upon, we'll see a particular case or a demo case that can actually explain the thermal comfort scenario using SimScale. And up next, we'll look into the live demonstration. So I will jump into the SimScale's platform and show you how these simulations can be actually set up and also how we can extract information from the simulation results. And finally, we'll look into some of the key results that might be valuable for a thermal comfort study and move on to a Q&A session. And at this point, I would like to actually mention again, if you guys have any questions, please use the question session or the question section in your webinar to ask your questions. We will get back to the questions at the end of this session. All right. So as a basic part of the introduction or to set the stage, we will be looking into two particular thermal comfort indices here. So the first one will be predicted mean vote, which will be mentioned as PMV in the coming slides, and also a predicted percentage of dissatisfied, so which will be mentioned as PPD. So as you can see here on the screen, we have two interesting images on the left. So the first one being the human comfort or the thermal comfort at the center and surrounded by some of the parameters. So a thermal comfort for a human or an occupant will be defined based upon certain parameters as shown here, such as metabolic rate, clothing insulation, humidity of the environment, the air speed that is prevailing, the air temperature, and also the radiant temperature. So let's see what or how a CFD solution in specific SimScale can help to achieve these kind of results or to compare different designs that can give you a good idea about the thermal comfort of a considered space. So considering all these parameters with CFD, you can actually simulate some of the parameters. One such parameter will be the airspeed. So using a CFD simulation, you can get a speed of air or the air distribution around a particular space or a classroom in our case, and also what kind of temperature will be there inside this particular classroom space. You can also add inputs to metabolic rate, the clothing insulation, which means if you are testing a classroom, then this will be a nominal clothing insulation. So students will be wearing a particular set of dresses, and we can give a particular value for this insulation to account for this thermal comfort. And also the humidity and radiant temperature, which can also be set as a parameter in our simulation. And once when these things are set, what can we get out of it? So the next image you can see is a ratio between the PMV and the PPD. So what you see on the screen as in the legend is a 7 scale specific to thermal comfort, starting from -3, which means the colder part, and also it ends at +3, which is the hottest range that we can actually allow for a thermal comfort study. So what these parameters actually define or how it is actually devised. So on the right, you can see for the predicted mean vote, we do have certain standards that could account for the thermal comfort. Two main important standards that we are going to look into are ASHRAE 55 and also ISO 7730. So based upon this one, if you look at the ranges that can be allowed for a thermal comfort, it should be from -0.5 to 0.5. So looking at the graph, you can see this is somewhere around the neutral region where the occupants feel really comfort. And anything beyond these limits will actually make the thermal comfort worse, or the occupants will face a local discomfort because of the temperature and also other factors included here on the left. And this goes the same for the PPD. So anything, PPD is just the percentage of people discomfort or a local discomfort the people are actually facing. So if you take a vote of the percentage of people who are feeling discomfort, this gives you the value of PPD. And this will be to comply with standards. There should not be any point in the space that we are going to analyze above 20% of PPD. So anything above 20% of PPD means that there are people who are feeling discomfort. So this gives you a brief introduction of what we are going to expect from a simulation and also a good background on how a thermal comfort study would look like. With this, we'll move on to the next. The next will be the demo case that we are interested in, or we will be actually demonstrating today with SimScale. This case is actually a case study done by one of our customers, Ramboll UK. This case study is done in the Queensferry High School, and we actually took one particular classroom for the thermal comfort study. So at this point, I would like to shout out for Ramboll UK for giving us a wonderful case study with SimScale. Okay, let's take a look into the synopsis. So what we're trying to do here with this classroom. So on the right, you can see this is an entire school premises which was simulated. And right now for the demo purpose, we'll be considering or focusing on this particular classroom. So here we are going to see if this classroom is in particular compliance with this ASHRAE 55 standards. Yes, just to define the CFD statement, we do have some problems that we can actually get answers from this CFD simulation. The first one being whether this classroom comply with the thermal comfort criteria or not. The second one being the temperature distribution. So we want to check whether the temperature is maintained between 25 to 27 degrees Celsius. And the third one being the airspeed, which can be also a result of a CFD simulation. And this we want to see if the range is between 0 to 0.2 meter per second. So now that the problem is well defined, let's take a look at the simulation and see what kind of results we can actually get from this particular classroom setup. Yeah, touching upon the first step in simulation. So we need to have a good CAD geometry to make the simulation work smoothly and also efficiently. So for this kind of analysis where you want to study the thermal comfort of a classroom, these are the CAD details that we would require to make sure we include all the simulation parameters. Up first, we should need the details of the human models. In case if you're simulating along the human models, this can be easily devised or designed as a cube with a particular heat source. And also, if there are a lot of furnitures which might affect the air velocity or distribution, then you would have to actually include the furniture into the CAD system. And the diffuser inlets. So the inlets and outlets are pretty much the only mandatory requirements for a simulation. So in our case, we do have a diffuser, which is designed like this, as you can see on the screen. And also there are two outlets, which are shown in red color and marked as 4. We do have some radiant panels, which means the lighting surfaces, which is important because the lighting might emit some of the heat and this might affect the temperature distribution inside this classroom. So we need to model them as surfaces also, as you can see marked with number 6 in blue. All right, now that we have the details required for such simulation, we can actually see how this can be set up using SimScale. So for this particular session, I will move on to the live demonstration, which means I'll be opening SimScale and showing you how this looks like inside SimScale. I'm going to minimize the screen and jump on to the actual simulation or the platform. So what you can see here is the SimScale platform. So those who have never seen or used SimScale, this is how SimScale looks like on a browser. So this can be easily accessed via simscale.com, and then you can create and run projects on your own. So all the projects that you create with a professional subscription will be kept private. And we do have something called a public community where hobbyists and students can actually do some simulations, which will be public to everyone. Yeah. Just to give a brief introduction on the platform, on the left, what you can see is the simulation tree. And on the top, you can see the geometry. So whatever geometry you upload to SimScale platform will be listed out here. And whatever simulations you do on the geometries will be listed out here. On the right, what you can see is a geometry tab. where you can see the parts and also the faces of the CAD models that you have included. So for our case, we just have only one solid part, which is going to act as a fluid region. So that is shown here. And at the center, what you're looking at is the post-processing scene of SimScale. So you can see some of the view modes and also rendering modes, selection modes, where you can select volume or either a face, and also the animation tab, where you can start playing an animation or changing the time steps of your simulation. On the right end, you can see something called inspect point. When you click this one, whenever you have some results on your screen, you can inspect any point in your domain to see what kind of value we have at a particular node or a particular domain. Turning this off. And we do have a toggle bulk calculator, which means if you press a surface and click this on, you will see the minimum and maximum temperature or any other variables that is plotted on this surface. You do have an option to take screenshot in case if you want this image to be published into one of your reports, you can use that. And on the left, what you see under filters is the post-processing capabilities. So when I press add filter, you can see we can add a cutting plane, just as like I did. So if you turn on the cutting plane, you can actually put a cutting plane inside the domain. And let me open the settings for this one, and you can move the position of the cutting plane at any point inside the domain to check what's happening at different locations. I will turn off this cutting plane. And what you're looking inherently on the screen is an ISO volume. So an ISO volume actually allows us to put a range to the particular variable that you want to plot. So in our case, we have selected temperature, and we have put a range of 300 Kelvin to 373 Kelvin. So anything between this range is plotted here on this particular visualization. In case if you're not familiar with Kelvin, you can actually change the units here under the legend. So you can change to degree Celsius, Fahrenheit, or radian. All right. You can also plot a particle trace starting from one of your inlets or outlets. So what you can see here, just to make the visibility higher, I will turn off the color to solid color. And what you're seeing here are the particle traces from the diffusers into the system. And when you press animate, this is going to animate the airflow of the results. So you can see whether there is a recirculation region or if there is a region where the air movement is not enough for the thermal comfort. So these are some of the options that you can use with the post-processing, and we will look at the key results which we have already extracted when looking at the setup, after looking at the setup. All right, at this point, I would like to actually remind the attendees that if you have any questions, please feel free to actually put that into the question section. All right. Now that we have seen the post-processing capabilities, now we can move on to this particular setup. So I will start from the geometries. So what you see here are multiple geometries that we can upload into the same project. So you can do it by simply clicking on the plus button. You can drag and drop your geometry. SimScale do support many formats like Parasolid, or native formats like SolidWorks, Autodesk Inventor, Rhino, CATIA, Creo, NX, Solid Edge, and Revit also. So you can simply drag and drop your CAD model or click on import from computer to select from a particular location. Once the CAD model is done, you can press the plus button near the simulations and go for convective heat transfer, which is the module we need for thermal comfort. And when you press this, you will get a simulation tree with the CAD model that you have selected. So you have red circles and tick marks, which means red circles are to be addressed before starting the simulation. And this includes the material properties. So for our case, we select air. And then you can select the fluid region that you want to assign. And up next, you have to set the boundary condition where all the physics of this model has to be set, just like the inlet, outlet, or any wall condition with a particular temperature on it. I will jump on to the previous setup, which we already have based on this one. So here the geometry is selected, material is selected, and also we have particular velocity inlets, pressure outlets, and heat sources for people, lights, and computer. So once when these boundary conditions are set according to your requirements, you can simply go ahead and start your simulation. Once when you press this simulation run or start the simulation, you will see a resource estimation. So it says that the simulation is going to take a particular amount of time to finish and also the computing resource that is required for this analysis. You can simply press start, and this will push your job to the cloud system we actually host. And in case if you have a particular change that you want to make, you can simply change the boundary condition. Let's say -2 meters per second, and save this one and start another run. So this way you can actually simulate multiple scenarios at the same time. And by the end of particular time, you will get the results of all the simulations. We do have something unique for our support, which means that on the right, you have a chat bubble where you can ask questions. Send us a message on your particular specific question. We'll reply to that within a few minutes. So this is pretty much useful when you're starting to use a new tool or starting to use SimScale. All right, I hope I covered most of the settings that is required for this analysis type. I will quickly jump onto the slide deck to show you some of the interesting results, and then we can discuss on the questions that we have already got. All right, at first you can see the velocity distribution through the diffusers. So in case if you're modeling a diffuser, then you can take a deeper look into the diffuser and change the modeling designs. And next you can see a cutting plane or a slice at the human sitting level. And here you can see the velocity is well within the range of the, the standard or the criteria. Up next, you can see the same cutting plane with the temperature distribution. And here you can see the temperature range is in yellow region, which means it is well maintained between 25 and 27 degrees Celsius, which is in compliance with the thermal comfort standards. And you can take a look at the PMV. And here the green color means that it is almost near to neutral, which means people or occupants inside this classroom are really comfortable. And finally, you can also plot the percentage of dissatisfied PPD value. And here you can see, except from the occupants' faces or surfaces where the actual heat generation is happening, everything is under blue color, which means under 15 to 10%. So this is well maintained at a particular thermal comfort. So this way you can actually use these results from CFD to analyze your thermal comfort of any particular premises, not just a classroom, but an office or any workshop or anything. So that is all regarding the results we would like to discuss. And let's move on to the question and answers section. I will also hand over the presentation to Steve for the questions.
That's great. Thank you very much, Ajit. That was an excellent presentation. So thank you to everyone who's attended. It's fantastic to see so many of you, and we've got a good number of questions come in. So let's get through as many of these questions as we can in the remaining time. So Ajit, the first question is, which 3D software is the best option to import for the simulations? So I think someone's asking what CAD is the best to import.
Okay, just to answer this question, since SimScale is based on a Parasolid CAD mode, so anything which is related to Parasolid works the best. So, and apart from that, we do support other CAD formats from SolidWorks, Autodesk Inventor, and Autodesk Inventor and Revit. So anything that is of native format is the best for the CAD tool. I hope that answers the question. Yeah.
Okay, great. And another question is around parallel simulations. So somebody's asked how many simulations can be run at one time?
This is really a good question. Since we are cloud-based, there is no actual or hard limit on the number of simulations that we can actually start at a particular time. So each simulation that you are going to start will be considered with a different set of processes. So there is no particular or hard limit on number of simulations at one time.
Yep, great. We really leverage the capabilities of having the cloud hosted software there. You can run as many as you like.
Exactly.
So another question someone's asking is it possible to test SimScale? Can they have a trial?
Sure, this is something possible with SimScale. So what we do for these scenarios is that we will set up a individual or separate call with you, and we want to discuss about what you want to test so that we can give you a professional test license for you guys. So you can test out the SimScale version and also reach out to us for any support or technical questions. So this is something possible with SimScale.
Great, great. And another question that's come in is around this actual simulation and how many core hours this took to run. Approximately how long did this take, Ajit?
All right. With the automatic core selection, this simulation took around 2 hours to finish, and also it took around 100 core hours for this particular simulation.
Okay, excellent.
So this is on general scale for all of the thermal comfort studies that you can do with SimScale.
Yeah, and you could run as many of those simulations at the same time as you liked. So in 2 hours, you could run 10 parallel simulations if you liked. Okay, so we've got a couple of minutes left to answer a few more questions that have come in. One of the questions that's come in is around actually importing the CAD. Someone's asked whether we should import the solid model or the fluid region for these kinds of simulations.
That's actually a good question. So for this kind of analysis, you can either directly import the fluid region, as we did in the demo, or you can import the solid model and then prepare the fluid region within SimScale. So we do have some geometric options that I can show you quickly on the screen. So under geometry, you can see we do have a certain model which is of solid. So you can see everything inside. So you have multiple solids. So you have something called open inner region where you can set the bounding faces and also the faces which are present inside. This will generate the fluid region automatically within SimScale. And just to show you how it looks like after the fluid region, you can see this blue color region, which means that it is a fluid region without any solids, but just the fluid. So you can import either a fluid or a solid region.
Great, thank you, Ajit. I apologize if we haven't had the time to answer your question that you sent in. We've had too many questions to be able to answer them all live, I'm afraid. But we've got your details and we will follow up on the questions to give you a detailed answer. So thank you very much to everyone who attended. It's fantastic to see so many of you attend.
Thanks, attendees. Have a nice day. Bye-bye.
Thanks. See you soon.